The last section in this chapter is about graphing radical functions, and specifically we're going to look at square root and cube root functions, which we touched a little bit on from the homework yesterday. And one big idea that reoccurs is the transformations of functions. So maybe pause the video at this point and think about what each of these equations would do to the parent graph and how it would move that parabola y equals x squared. The first one, if I am subtracting 5 from x and it's attached to the x, that's actually going to move the graph 5 to the right. You could think, here your vertex was 0, 0. Now if I plug in 5, that's when I'm going to get out 0. So if I'm subtracting 5 and it's attached to the x, it's going to move the graph 5 to the right. If I'm subtracting 5 and it's not attached to that x squared, then that's going to move the graph 5 down. You could see here if I plug in 0 for x, 0 squared minus 5, your vertex would actually be down 5 at 0, negative 5. The negative out front, that would actually reflect the graph over the x-axis. If I have the 5, that's going to make the graph narrower. So if I input an x, whatever y value I got before, now that y value is going to be 5 times as large. And if I have a 1/5 out front, that's going to widen the graph. The 5 we refer to as a vertical stretch. If I multiply by something in between 0 and 1, that's going to be a vertical compression. So with this in mind, let's look at our parent functions, the square root function and the cube root function. So if I go ahead and I graph these functions, whenever I'm graphing the square root function, I want to maybe input values that I could take the square root of. So the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. And I could plot these points, and I should get a pretty nice shape for my graph, y equals the square root of x. Now what's the domain? What are all possible x's? Well, the smallest value I can input is 0. I cannot take the square root of a negative and get out a real number. And then I can certainly take the square root of any positive numbers. However, these are the numbers that give me out whole number solution. So those are the numbers that are kind of nice to input into your table if you're graphing by using a table. The range, what's going to come out? Well, there's no way I can get out a negative number, but I will get out positive numbers. So this graph is actually increasing, although it's increasing pretty slowly, increasing. So the smallest y value or the lowest I see my graph hit is I can get out 0 for y. And then I can also get out positive numbers. I can't take the square root and get out a negative number. So if I were making a table for the cube root function, well, I'd probably want to pick values that I can take the cube root of. Now remember, I can take the cube root of negatives. So I should be able to input anything in for x. The cube root of negative 8 is negative 2. Cube root of negative 1 is negative 1. Cube root of 0, cube root of 1. Cube root of 8 is 2, because 2 cubed is 8. And then if I plot these, I should actually get this nice smooth curve. And remember, this is actually the inverse of the parent function, y equals x cubed. So it sort of looks like that y equals x cubed graph, but it's just reflected over the line y equals x. The range then, what's going to come out for y? Well, if I'm taking the cube root, I can get out positive numbers, I can get out negative numbers, I can get out 0. So my range, I should actually be able to get out anything. And if you look on this graph continues forever and ever, left and right, and it'll continue up and down forever and ever as well. So the domain and range are all real numbers. Therefore, if I'm graphing a square root function, it should look generally like this. If I have a cube root that I'm graphing, I should generally get, this shape right here. So first example, if I graph the function y equals the square root of x minus 2, I might make a table and think about, well, what are some nice values to take the square root of? So square root of 0, square root of 1, square root of 4, square root of 9. And then the square root of 0 is 0, but then I want to subtract 2. So square root of 0 minus 2, that would actually give me negative 2. So 0, negative 2 would be the first point on my graph. If I input 1 into the function, I'd get the square root of 1 minus 2. So 1 minus 2, or negative 1. So if I input 1, I'm going to get out negative 1. If I input 4, square root of 4 minus 2, well, square root of 4 is 2. 2 minus 2 is 0. So if I input 4, I will get out 0. If I input 9, square root of 9 is 3. 3 minus 2 is 1. So if I input 9, I'm going to get out 1. And now if I plot these points, I should have the graph of my function. 0, negative 2, 1, negative 1, 4, 0, and 9, 1. And all I need to do is connect this. There's the graph of my function. Now, how does this relate to the graph of the parent function? So let's go back. This should look similar to the parent function, except, make a connection here. If I am subtracting 2 and it's not attached to that square root, it's not attached to the x within the square root, that's just going to bump the parent function down 2. So the parent function, if I move it down 2, I will actually get this new graph. That would be another way to graph this function. Now what's the domain? What can I plug in for x? Well, whatever's under the square root has to be greater than or equal to 0. So x can be 0 or larger. And now what's going to come out? Well, on my parent function, I said, well, I'd get out anything from 0 to infinity. But since I'm actually subtracting 2, notice that this is the lowest the graph dips on the y-axis. So I can actually get out negative 2, and then it's going to continue upwards. I'd be getting y values that get increasingly larger all the way up to infinity. So subtracting that 2 bumps the graph down 2, and therefore bumps my range down 2 as well. Okay, so what do you think would happen here? If I'm adding 4 to the x value within the radical sign, any guesses? This should actually move the parent function left 4. Now, if I'm inputting values, I'd be thinking, okay, well, I know how to take the square root of 0 and the square root of 1 and the square root of 9. So here's kind of my thought process when I'm making a table. I want to take the square root of, 0, or the square root of 1, or I know how to take the square root of 4, or the square root of 9. So therefore, if I solve these equations, like if I plug in negative 4, or if I plug in negative 3, or if I plug in 0, or if I plug in 5, those would be kind of nice input values. Okay, so here's my table. I'm going to plug in these values. Negative 4, negative 3, 0, 5, and I should get out nice whole numbers for y. All right, so here's my table. Go ahead and input these. Let's see what you get out. So here's my table. Here are my points. Negative 4, 0. Negative 3 gives me out 1. 0 gives me out 2. If I input 5, I get out 3. There we go, 5, 3. And the next kind of nice value, I guess, would be if I inputted 12, the square root of 12 plus 4, square root of 16 is 4. But that's going to be off my graph, so I will just stop here and connect, and there's the graph of my function. So again, it's useful to know what my parent function looks like and what this transformation does if I'm adding 4. That actually bumps the graph left 4, which ties into all that stuff we talked about first semester. Now my domain, well, okay, whatever's under the square root can be greater than or equal to 0. So x plus 4 can be greater than or equal to 0. That means x is greater than or equal to negative 4. And yep, that looked like the smallest number that I could input. That gave me out 0 under the radical sign. So smallest number I could input is negative 4. Anything smaller would give me a negative number under the square root. And I can plug in anything larger. Graphically, the furthest left my graph is negative 4, and it continues on to the right. The range, I want to look at the lowest this graph dips. Well, the lowest or the smallest y value I can get out is 0. And then so this is going to keep going upward towards infinity. So there's my domain and range for this function. So here's another one to try. If I'm looking at my parent function, I might be thinking, well, what does that minus 3 do? What does the plus 1 do? What does the negative do? And what does the 1/2 do? So maybe pause the video and think about this for a moment. That negative 3 should move things right 3. And actually, well, I should probably go with the reflections first. So the negative out front, this is actually going to reflect it over the x-axis. So reflect over x-axis. The 1/2 is going to cause a vertical compression. So the negative reflects over the x-axis, the 1/2 is going to cause a vertical compression, or the graph is going to be squished vertically. The 3 is going to move the graph 3 to the right, since that's attached to the x. And since the plus 1 is outside of the square root sign, the graph is also going to move 1 up. So if I do these 4 things to the parent function, I should get the graph of y equals negative 1/2 times the square root of x minus 3 plus 1. So at this time, I'm going to make a table. Think about what x values you could plug in that would cause, kind of nice numbers under the radical sign, and then let's compare our graphs. So pause the video and give this a try. So first thing, I can take the square root of 0, so 3 minus 3 is 0, times negative 1/2 is 0, plus 1 gives me 1. 4 would give me 1 under the radical sign. Square root of 1 is 1, times negative 1/2 plus 1, that gives me out 1/2. If I plug in 7, I get the square root of 4, which again is a nice number. 2, negative 1/2 times 2 is negative 1 plus 1 gives me out 0. 12 would be kind of the next nice number, because that would give me 9 under the square root sign. But already there I'm off the graph. So if I plot these 3 points, 3, 1, 4, 1/2, and 7, 0, my function should actually look like this. What do you notice? This opens upside down because of the negative sign. The graph is compressed vertically, so it's not quite as steep. The vertex, or well, I shouldn't say vertex, but the starting point is moved 3 to the right and 1 up. So my domain now, whatever's under the radical, has to be greater than or equal to 0. So x is greater than or equal to 3. So smallest number I can plug in would be 3. Anything smaller than that would give me out a negative under the radical sign. And then the graph continues to the right. I can plug in anything larger than 3 and get out a real number for y. Range, the lowest this graph goes. Well, actually, if you see the trend, this is going to keep going lower and lower and lower and lower. And this is going to go down towards negative infinity. So it will keep going lower. And the highest point now, the highest y value is going to be right here. The largest y value is 1. So I'm actually going from negative infinity to 1 because this negative sign out front causes the graph to flip. So let's look at one last graph. Let's graph a cube root function. The first thing to notice about this graph is the parent function, y equals the cube root of x, is going to look something like this. It's that sideways graph of y equals x cubed, since it's the inverse of y equals x cubed. The 2 out front means it's going to be vertically stretched. So this might end up being wider than the original parent function. The +1 should actually move this graph 1 to the left, since that's attached to the x under the cube root. And then since the -4 is outside the cube root, that should actually move the parent function 4 units down. So have some idea in your mind of what this function is going to look like before you actually graph it. Then if I'm making a table of values, well, if I'm taking the cube root, think of numbers that would be nice to take the cube root of. So for instance, the cube root of 8 is a nice number. So if x plus 1 is 8, that would produce a nice integer value. If the number under the radical sign is 1, I could take the cube root of 1. I should be able to take the cube root of 0. I should be able to take the cube root of -1. I should be able to take the cube root of -8. So think of what x values you would have to input under the radical sign to get out these perfect cubes and start making a table. So at this time, maybe pause the video, think of what x values would be nice to input. So here's my table. These are the x values that I picked, -9, -2, -1, 0, 7. Why did I pick these x values? Well, if you solve those equations I just had written on the previous couple seconds, -9 plus 1 is -8, and I can take the cube root of -8 and get a whole number. -2 plus 1 is -1, that's also a perfect cube. 0 is a perfect cube, 1's a perfect cube, and 8's a perfect cube. So now at this point in the table, just go ahead and simplify. So like this, for instance, would be 2 times the cube root of -8 minus 4. The cube root of -8 is -2. So -4 minus 4, that would give me out a y value of -8. And you can proceed and simplify the rest of these perfect cubes. So I'm going to do that. If you want to give it a try, you can pause the video. So if you simplify all of these are the y values. And then I just went ahead and plotted the points. -9, -8, -2, -6, -1, -4, 0, -2, and 7, 0. Those should be on your graph. Yep, this gives me the shape I was generally thinking I would come out with. It resembles the parent function. And note, this center point here, this used to be at the origin. Now that point is moved 1 to the left and down 4 from where it originally was on the parent function, matching to what I thought would happen. And then the graph is vertically stretched. The other thing to note when you're graphing it is there should be some symmetry to graph. So if that's kind of my center point, if I go 1 to the right, 2 up, I'd get that next point. If I go 1 to the left, 2 back, I'd get that next point. So the graph should be nice and symmetrical.